In this example, we are given a contingency table split by both preferred subject as well as gender, and are asked to test the independence of the two variables. There are two rows of data, so R is equal to 2, and there are 3 columns of data, so C is equal to 3. A total sample size of 100 students is observed, so N is equal to 100. Alpha is given to be 5%. Since we want to test if there is an association between the two variables, our null hypothesis should state that gender and subjects are independent of each other. The alternative hypothesis should then state the opposite, which is that they are not independent of each other. Based on the scenario, we came up with a null and alternative hypothesis. Since we are testing the independence of the two variables, we'll use the chi-square distribution for our analysis. Using alpha at 0.05, the right tail area becomes the rejection regions. To get the degree of freedom of R minus 1 times C minus 1, we saw earlier that R is equal to 2 and C is equal to 3. Hence, df is equal to 2 minus 1 times 3 minus 1, which is equal to 2. Next, to get the critical chi-square value, we use the chi-square table. Look for the degree of freedom of 2 and the right tail probability alpha of 0.05. Pick up the corresponding value of 5.991, and that becomes the critical chi-square value, which separates the rejection and the non-rejection region. Next, we find the test statistics. In order to get this value, we need to do some calculation in a separate area. Using the given contingency table, we get the observed frequencies O sub ij's. Next, we find the marginal probability P sub j for each column. To get P sub 1, we take the column total of 40 and divide it by the overall total of 100 to get 40 over 100. To get P sub 2, we take the column total of 30 and divide it by the overall total of 100 to get 30 over 100. Do the same for P sub 3. To get the expected frequency E sub ij, the formula is given as P sub j times N sub I naught. For example, to get E sub 11, we take the probability of the first column times the total for the first row to get 40 over 100 times 60, giving rise to 24. To get E sub 12, we take the probability of the second column times the total for the first row to get 30 over 100 times 60, giving rise to 18. Do the same for the rest. The total for each row and each column should tally with the observed frequency table. Next, we find chi-square star. The formula for chi-square star is given by this formula. But first, we must find the squared difference between the observed and the expected frequency, divided by the expected frequency for each category. For the first column and first row, we substitute O sub ij with 25 and E sub ij with 24 to get this value. For the first row and second column, we substitute O sub ij with 12 and E sub ij with 18 to get this value. Do the same for the other categories. Finally, to get the test statistics, add all the values together to get 8.576. So we have found the test statistics chi-square star to be equal to 8.576, which is somewhere around here. Since it lies in the rejection region, H0 is rejected at alpha equal to 0.05. And we conclude that there is a strong evidence to show that gender and subject are not independent of each other at 5% significance level. Now that we have rejected the null hypothesis, further analysis may be needed to find out where the difference between the observed and the expected values have come from. To analyze that difference, we take O sub ij minus E sub ij to get the difference. Do the same cell by cell to get this table. For female students, the observed frequency for science falls short of the expected value, but the observed frequencies for art exceeds the expectation. Hence, we can infer that female students prefer art to science. For male students, the observed frequencies for science exceeds the expected value, but the observed frequencies for art falls short of the expectation. Hence, we can infer that male students prefer science to art in this case.